Welcome to Brain Vision.
Our question is question 178 of chapter 9. The electricity and the process heat requirements of a manufacturing cycle are to be met by a cogeneration plant existing of a consisting of a gas turbine and a heat exchanger for steam production. The mass flow rate of the air in this cycle, the back-work ratio, thermal efficiency, the rate at which steam is produced, and the utilization of energy efficiency for the cogeneration plant are to be determined. As we will consider here, the kinetic and potential energy changes are negligible. So, for an ideal case, enthalpy is a function of temperature only. So, for the process 1 to 2, that is compression, we will write the properties. At temperature T1, that is 20 degrees centigrade, value of H1 is 293.5 kilojoule per kg. At temperature T1, 20 degrees centigrade, and pressure P1, 100 kilopascal, value of S1 entropy is 5.682 kilojoule per kg dot K. Pressure P2 is equals to 1000 kilopascal. So S2 is equals to S1, that is equals to 5.682 kilojoule per kg dot K. At these two values, value of H2 is equals to 567.2 kilojoule per kg. So our thermal efficiency for a compression is H2S minus H1, H2 minus H1. That is 0.86 is equals to 567.2 minus 293.5 divided by H2 minus 293.5. So from here, value of H2 is equals to 611.8 kilojoule per kg. Now for the process of expansion, 3 to 4, that is expansion. Temperature T4 is equals to 450 degree centigrade, at which the value of H4 is equals to 738.5 kilojoule per kg, and thermal efficiency is equals to H3 minus H4 divided by H3 minus H4s. That is equals to 0.88 H3 minus 738.5 divided by H3 minus H4s. This is 38. H3 is equals to 1262 kilojoule per kg. Temperature T3 is equals to 913.2 degrees centigrade, and entropy is equals to 6.507 kilojoule per kg dot K. At temperature T5, is equals to 325 degrees centigrade, at which the value of H5 is equals to 605.4 kilojoule per kg. So our net work output will become equals to, that is, work done by a compressor inward is equals to H2 minus H1, that is 611.8 minus 293.5. Answer would be 318.2 kilojoule per kg. Work done by turbine outward is equals to H3 minus H4. Putting the values, we will get 523.4 kilojoule per kg. So our net work done become equals to outward work minus inward work. That is 520.4. Answer would be 205.2 kilojoule per kg. So the mass flow rate of air become equals to W net divided by power divided by work done. That is 1500 joule per second divided by 205.2. The answer would be 71311 kg per second. So now the back work ratio RBW is equals to WC input divided by work done per turbine output. That is 318.2 divided by 523.4. Answer would be 0.608. The rate of heat input and thermal efficiency can be calculated as rate of heat input, that is Qin, is equals to mass flow rate of an air into H3 minus H2. Putting the values, 7.311 into 1262 minus 611.8, this would be 4753 kilowatt. So our thermal efficiency become equals to net work done divided by heat input. This would be 1500 divided by 4753. Answer would be 0.3156. That is 31.6%. Now the energy balance and heat exchanger gives mass of an air into H4 minus H5 HW2 HW1, that is 7.311 into 738.5 minus 605.4 is equals to 2792 minus 64.47. So mass flow rate will become equals to 0.3569 kg per second. So now in the D part, the heat supplied to the water in the heat exchanger, and the utilization efficiency. Now heat supplied to the water in the heat exchanger is equals to mass flow rate HW2 minus HW1 is equals to 0.35692792 minus 64.47. Answer would be 973.5 kilowatt. So the effectiveness is equals to W0 plus QP divided by QE. Putting the values, that is 1500 plus 973.5 divided by 4753. Answer is 0.5204, that is 52.0%. That's our answer. Thank you.